So imagine you're just driving down the highway at like 70 miles an hour.
Right, totally relaxed.
Yeah, you've got the radio on, you're just coasting along. But I mean, underneath you, there's this solid steel drive shaft that is just spinning violently, transferring literally hundreds of horsepower from your engine to your wheels.
It's actually kind of terrifying when you think about it.
It is,
Uh-huh.
because we tend to think of a mechanical system like that as having, absolute rigidity. Like we look at a car engine or some huge industrial pump, and we just see this solid, unmoving block of metal that just magically does work.
Yeah, we project this illusion of permanence onto heavy machinery. From the outside, industrial metal looks completely indestructible.
Right. But what if I told you that that solid steel rod underneath your car
Mhm.
is actually twisting and bending and basically constantly on the verge of ripping itself apart?
Exactly. The deeper you go into the actual physics of how it operates, the more you realize it's in this constant fight against catastrophic failure.
And that fight is exactly what we are exploring in today's deep dive. We've got this fascinating stack of honestly incredibly detailed, handwritten mechanical engineering notes right here on the table.
They are very dense.
Yeah, super dense. They cover the physical foundations of machinery, so transmission shafts, keys, and couplings. But reading through them, I gotta say, it didn't really feel like a dry textbook. It felt more like a mechanical anatomy book.
Oh, that is the perfect way to frame it, actually, because we're really looking at the hidden biological structures,
Huh?
like the bones, the ligaments, the joints that actually power the physical world around you.
Exactly. So our mission today is to decode that hidden anatomy for you. We're going to take all these dense engineering concepts and stress formulas and metallurgical diagrams and translate them into a vivid understanding of how engines actually transfer all that massive power to machines without just completely destroying themselves.
Because the forces we're talking about are immense. I mean, if an engineer doesn't design these components with a really granular understanding of how metal behaves under microscopic stress, the machine doesn't just stop working. It basically explodes.
Wow. Okay, so let's start with the spine of the machine, right?
Mhm.
The transmission shaft. Because if you want to move power from, say, a motor over to a pump, you need this core rotating rod.
Right, the central bone.
Yeah. And the notes define it simply as a rotating machine element, circular and cross-section, that supports transmission elements like gears and pulleys. Sounds pretty straightforward.
It does, but the physical geometry of that rod is where the engineering immediately gets, incredibly meticulous
Mm.
because they aren't just straight uniform cylinder.
Right, it's not just like a wooden dowel.
Exactly. If you look closely at a transmission shaft, it's stepped.
Yeah, like the maximum diameter is always right in the dead center,
Yeah.
and then it kind of tapers down in deliberate steps to a minimum diameter at the two ends.
Which makes sense visually, right?
Yeah, I mean, the thick middle is bearing the brunt of the heavy gears hanging off it, while the thinner ends are just there to slip into bearings to let the whole thing spin.
But those steps also provide these physical shoulders. So
Yeah.
when you slide a heavy gear onto the shaft, it hits that step and just stops. It lets you precisely position things. But here is the critical detail in the notes. At every single step where the diameter suddenly drops, you cannot just machine a sharp 90-degree corner.
Because it would just snap.
Pretty much. The notes heavily emphasize the use of fillets, which are these smoothed, rounded-off transitions between the steps.
Oh, right, because a sharp microscopic inner corner would just be like the absolute perfect place for a crack to start forming under pressure.
Exactly. That sharp inner corner acts like a microscopic wedge. Engineers actually call it stress concentration. So every single time that shaft revolves, the physical twisting force flows through the metal.
Like a current.
Yeah, like a current. And when that force hits a sharp corner, it bunches up and multiplies. It basically acts like a magnifying glass for stress, eventually just tearing the crystalline structure of the metal apart.
Wow.
So rounding it out with a fillet allows the force to flow smoothly through the transitions, kind of like water flowing around a smooth river rock rather than crashing violently into a jagged cliff.
That makes so much sense. I was actually reading about a historical equivalent to this, the de Havilland Comet. It was one of the first commercial jet airliners.
Oh, the square windows?
Yes, they had these square passenger windows, and the sharp corners caused massive stress concentrations. The metal fatigued, and the planes literally tore apart midair.
It's terrifying.
It really is.
Yeah.
So applying that same concept to a spinning drive shaft, it makes it super clear why those fillets are basically a matter of life and death.
It's the exact same physics. It's just applied to a rotational load rather than, cabin pressurization.
Hmm.
And because the loads are so extreme, the material itself has to be incredibly tough.
Yeah, and the notes get highly specific about the materials they use for this. For ordinary shafts, they list things called machinery steels, specifically pointing to these codes like 30C8 or 40C8.
Right.
And then for intense applications, they upgrade to 45C8 or specialized alloy steels. So for those of us who don't run a foundry, what do those numbers actually mean?
It all comes down to carbon. In those codes, the C stands for carbon, and the number relates to the percentage mixed into the iron, because carbon is basically the magic ingredient that turns soft iron into strong steel.
Oh,
So when you go from 30C8 up to 50C8, you're increasing the carbon content. And more carbon means a harder, stronger metal that can handle way heavier loads.
but there's a catch, right?
A massive catch.
Yeah.
As you increase the carbon to make it harder, the metal also becomes more brittle.
Well, so you're constantly balancing these two demands,
Yeah.
strength and rigidity, because the shaft has to survive axial tensile forces pulling on it and bending moments trying to snap it like a twig.
And torsional moments, which is that violent twisting force we talked about.
Right, so to figure out if a specific piece of steel will actually survive that cocktail of forces, engineers use this mathematical tool mentioned in the notes called Moore's circle.
Yes, more circle.
I was looking at the diagrams for it, and
Uh-huh.
honestly, it looks incredibly complex. How does drawing a literal circle help an engineer visualize physical stress?
Okay, so imagine plotting a graph. The horizontal x-axis represents the pulling and pushing forces, so tension and compression.
Okay. Yeah.
Then the vertical y-axis represents the twisting force, which is the shear. By plugging the operating loads of the machine into an equation, you plot points on this graph and you literally draw a circle connecting them.
And what does the circle tell you?
The radius of that circle instantly reveals the absolute maximum stress the metal will experience from any possible angle inside the shaft.
That is actually genius.
Yes.
But here's where I got a bit confused by the notes. They spend a solid page explaining how to use Moore's circle to calculate the maximum principal stress theory to find out when the shaft will break.
Yeah.
But then, almost immediately, they completely dismiss it. They state that the maximum shear stress theory is actually universally applicable for shaft design.
Right. They pivot completely.
Yeah. So if the principal stress math isn't what they use, why do they even teach it?
That distinction highlights a fundamental property of how different materials fail. So maximum principal stress theory is incredibly accurate, but only for brittle materials.
Oh, like glass.
Exactly. Or think of a piece of blackboard chalk or cast iron. If you take a piece of chalk and twist it, it snaps cleanly along a 45-degree angle. It fails under tension because the material literally gets pulled apart.
Oh, I see. But these transmission shafts aren't made of cast iron or chalk. They're made of medium carbon steel, which is ductile.
Precisely. Ductile materials do not fail by snapping or pulling apart. They fail by slipping. The internal crystalline layers of the steel literally slide past one another.
Ugh, just thinking about that makes my teeth hurt.
I know, right? That sliding, scissoring force is called shear. So the maximum shear stress theory is the universally accepted standard for shafts because it perfectly models how the physical structure of steel actually gives way when you twist it too hard.
So it's really about matching the mathematics to the physical reality of the specific metal you chose.
Exactly.
And speaking of physical reality, we really have to talk about the section on hollow shafts, because the notes just casually mention that a hollow shaft possesses more stiffness and more strength for the exact same weight as a solid shaft.
Plus, they handle vibrations way better.
Yeah, which blew my mind. Like, how does a tube outperform a solid bar?
Well, in a solid spinning rod, the material located at the dead center is doing almost no work when it comes to resisting a twisting force.
Really?
Yeah, all the mechanical leverage, all the heavy lifting is being handled by the material on the outer edges. So removing the dead weight in the center doesn't actually sacrifice the shaft's ability to resist torque.
You know, evolution figured this out millions of years ago. I immediately thought of bird bones when I read that.
Oh, that's a great analogy.
Yeah, because to fly, birds had to sacrifice internal bone volume to achieve this incredible strength-to-weight ratio without becoming, too heavy to get off the ground.
And engineers are just doing the exact same thing with steel. They use hollow shafts for massive ship propellers or deep hole drilling rigs where you absolutely need the strength, but you just can't afford the sheer mass of a solid block of steel.
But the trade-off, as the notes point out, is manufacturing complexity. Boring out the center of a 20-foot steel rod is, significantly costlier.
Oh, incredibly expensive. And to achieve the same total strength as a solid shaft, a hollow shaft requires a larger outer diameter, which obviously takes up more physical space in your machine.
Right, so you only use them when the weight penalty of a solid shaft is unacceptable, or when you specifically need that hollow center to, like, pump coolants through, like in those drilling rigs you mentioned.
Yeah.
Okay, so we have this massive, mathematically perfect steel bone to carry the power. It's stepped, the fillets are perfectly smooth, the carbon steel is selected, and it's hollowed out to save weight.
A masterpiece of engineering.
It is. But a smooth metal cylinder is practically useless on its own. If you just slide a gear onto it, the shaft will just spin freely inside the gear hole. No power actually transfers.
Right, it just slips.
So how do you physically force them to lock together without destroying that beautiful shaft?
Honestly, my very first thought reading this was, well, why not just weld the gear directly to the steel shaft and be done with it?
Welding seems like the obvious solution, for sure.
Mm-hmm.
But it introduces massive problems. First, the intense heat of welding can warp that carefully machined shaft and completely alter the metallurgical properties of that carbon steel, making it brittle.
Oh, right. It messes up the heat treatment.
Exactly. And second, machines break. Gears wear out.
Mm.
If you weld a gear to a shaft, you can never take it apart for maintenance or replacement. You basically have to scrap the entire assembly. Which brings us to the tiny mechanical linchpins of the industrial world, which are keys. A key is a small element used to temporarily connect a transmission shaft to a rotating machine element, like a gear or a pulley.
Its whole job is to transmit the torque and prevent any relativification while still allowing you to take the machine apart later.
But, and here's the massive catch-22 I found in the notes. To place a key between the shaft and the gear, you have to physically alter the shaft.
Yep, you have to cut a longitudinal slot right down the side of it, which engineers call a keyway.
This drove me crazy. We literally just spent all this time using Morse circle to calculate the exact perfect diameter of the shaft to ensure it survives the twisting force. We meticulously smoothed out the fillets to prevent stress concentration. And then, the very first thing we do is cut a sharp rectangular trench right into the side of it. The notes cite the ASME code, showing that just adding a keyway drops the permissible shear stress of the shaft by a full 25%. That is a massive weakening of the system.
It really is. It's the absolute essence of engineering compromise. You are sacrificing localized strength to gain systemic function. Yes, cutting the keyway weakens the shaft by 25%, and yes, the sharp corners of the keyway introduce the exact stress concentrations we were just trying to avoid with the fillets.
So how on earth do they get away with it on a factory floor? If it's 25% weaker, why doesn't it just snap?
Because they oversize the shaft.
Oh.
Yeah, an engineer calculates the mathematically perfect diameter for the load, and then they intentionally make the shaft much thicker and heavier, specifically to act as a buffer for the weakness they know they're about to introduce by cutting the keyway.
Okay, so you build a bigger bone knowing you're going to carve a notch into it.
Exactly.
Let's look at the actual keys they place in those notches, because they really range from simple friction fits to, like, heavy-duty mechanical locks. First, you have the saddle keys.
Right, saddle keys.
And the defining feature here is that you actually do not cut a keyway into the shaft at all for these. You only cut a slot into the hub of the gear.
So if there's no slot on the shaft for the key to grab onto, it's relying purely on friction.
Exactly. The saddle key just curves to match the shaft and sits tightly against it. My analogy for this is trying to open a really tight jar with your bare hands.
Oh, that's good.
You're relying entirely on the surface friction between your skin and the smooth metal lid to transfer your twisting force. And just like opening a jar, if the lid is stuck too tight and you push too hard, your hand just slips.
Yeah, right. So saddle keys are only suitable for light duty. For medium and heavy-duty industrial applications, relying on friction is just a recipe for a disaster.
So what's the upgrade?
The industry standard is the sunk key.
Right, with a sunk key, you are cutting a keyway into both the shaft and the gear hub. So half of the key's thickness sits inside the shaft, and the remaining half sticks up into the gear.
So now you aren't relying on friction. You're relying on the physical shear resistance of the metal key itself.
It's like putting down the jar and using a perfectly...
The Kennedy key is such an elegant solution for extreme heavy-duty applications. Instead of one key trying to handle all that torque, you use two square keys, and they are positioned exactly 45 degrees apart from the vertical center of the shaft.
And That angled positioning does two things, right? It splits the load, and it mechanically forces the gear hub into a perfectly concentric position with the shaft, making sure it doesn't wobble at high speeds.
Exactly.
But wait, what if you need a gear to not just spin, but to slide back and forth along the shaft while it's spinning? Like, I'm thinking of inside an automobile manual transmission where you are actively shifting gears.
A standard sunk key would just pop out or bind up under that kind of friction. So for sliding motion under high torque, you use splines.
Splines are fascinating. They're basically multiple keys, but they aren't separate pieces of metal. They are milled directly out of the shaft itself.
Yeah, the shaft ends up looking almost like a long extended gear, and it slides into a hub that has perfectly matching internal grooves.
It's so cool. It allows the gear to slide axially back and forth on the shaft while continuously transmitting just massive amounts of torque.
So we have the shaft to carry the power, and we have the splines and keys to attach the working gears, but there's a final structural problem here.
Right. What if we need to permanently join two completely separate machines together?
Exactly. Say you have a massive electric motor you just bought, and you need to physically attach its output shaft to the input shaft of a heavy industrial water pump.
Which is huge on a factory floor.
It is, and they also absorb operational shocks and vibrations. Rigid couplings, as the name implies, cannot tolerate any misalignment whatsoever.
Which brought up a major question for me. If flexible couplings are so incredibly forgiving, I mean, if they absorb shocks, dampen vibrations, and literally save your machinery if your alignment is slightly off, why do the notes spend the vast majority of the chapter focusing on rigid couplings? Isn't a flexible joint just objectively better in a chaotic, vibrating industrial environment?
It definitely seems counterintuitive, but it really comes down to scale, raw power, and manufacturing complexity. Flexible couplings have numerous moving parts and perishable rubber or spring elements.
So they break down faster.
Yeah, that makes them expensive to produce and requires constant maintenance. Rigid couplings are incredibly simple, solid pieces of metal. Because they don't flex, they have a vastly higher torque transmitting capacity.
So if you have a strictly controlled engineering environment, like, say, a concrete factory floor, where you can laser align the motor and the pump to perfect collinearity, a rigid coupling is actually the superior choice for moving raw, uninterrupted power.
Exactly. I like to think of it as the difference between wearing cushioned running shoes for agility versus solid steel-toed boots for heavy lifting.
That's a great way to put it.
Yeah.
Let's look at the simplest rigid coupling in the notes, which is the muff or sleeve coupling. My analogy for this one is putting a stiff medical cast over a broken bone.
Oh, spot on.
You take this hollow cast iron cylinder, slip it directly over the two abutting ends of the shafts, and lock the whole rigid sleeve down with one incredibly long sunk key.
It's brilliantly minimal. There are really only two parts, the cast iron sleeve and the key.
Right, and the notes list its advantages. It's cheap, it's highly compact, and the external surface of that sleeve is completely smooth.
Which is actually a massive safety advantage because there are no spinning bolts on the outside to catch a factory worker's sleeve and pull them into the machine.
Ugh, yeah, that's a grim thought. But the downside is the assembly. You have to physically pry the machines apart to slide the sleeve on or off. And if your shafts are even a fraction of a millimeter out of alignment, forcing that rigid cast iron sleeve over them induces this permanent bending force that will just slowly destroy the bearings of both machines.
Which is exactly why, for larger shafts and heavier loads where you can't just wrestle a sleeve onto the metal, the industry relies on the rigid flange coupling.
Right. The flange coupling looks basically like bolting two heavy dinner plates tightly together, back to back. You take a left-hand cast iron flange and key it to the driving shaft. You take a right-hand flange and key it to the driven shaft. Then you bring the two flat faces together and bolt them in a circle.
Right.
But since we literally just established that rigid couplings require absolute perfect laser alignment, how do they guarantee that two plates are perfectly centered before they bolt them down? I mean, you can't just rely on the bolts themselves. There's always a tiny bit of wiggle room in a bolt hole.
Oh, relying on bolts for alignment is a classic engineering mistake. The sheer force of the spinning shafts would eventually snap the bolts entirely. Instead, they use a mechanical interlocking feature machined directly into the faces of the flanges.
The notes call it a spigot and recess. One flange has a tiny, precise cylindrical projection, the spigot, sticking out of its center face. The opposite flange has a perfectly machined hole, the recess.
It works exactly like building with Lego bricks.
Yes, you don't just push two flat, plastic blocks together and hope they stay aligned by friction. The little studs on top of one block physically interlock with the tubes underneath the other.
And that spigot and recess physically force the two heavy steel shafts to share the exact same axis before you even tighten a single bolt.
It's such an elegant solution. The interlock takes the rotational shear force completely off the bolts, making sure the entire assembly acts as one solid, perfectly located mass.
And speaking of the bolts, there is a vital safety feature dedicated to them in the notes as well. They contrast unprotected versus protected flange couplings.
Right.
So in a protected coupling, the cast iron flange isn't just a flat plate. It has these circumferential rims, basically these heavy metal lips, that project outward and completely shroud the revolving bolt heads and nuts.
Because when you're dealing with a flange that might be like 2 feet wide, spinning at 1,000 revolutions per minute, that outer edge is moving incredibly fast.
Very fast. And
Yeah.
under that immense torque, bolts can fail.
Right. The notes specifically point out that if a bolt snaps while the machine is running at full load, those heavy broken pieces of metal are basically flung outward by centrifugal force.
Yeah, so in an unprotected coupling, a broken bolt head becomes a high-velocity projectile shooting across the factory floor.
Which is terrifying.
Yeah.
But with a protected coupling, the broken pieces dash violently against that internal rim and fall harmlessly down to the floor inside the shroud. Its mechanical design actually anticipating failure to save the operator's life.
It is a sobering reminder that engineering is never just about calculating maximum efficiency. A massive part of the discipline is designing the architecture of how a machine will fail when the forces finally overwhelm it.
Absolutely. Bringing this whole deep dive full circle, it really is a mechanical anatomy book. It's this symphony of interacting physical parts just holding back chaos.
That's a great way to put it.
The transmission shaft acts as the bone, mathematically sculpted with fillets to bear the immense twisting loads without fatiguing. The sunk keys and splines act as the ligaments, locking the components together through sheer physical resistance so power can actually transfer. And then the rigid couplings act as the permanent joints, that interlocking handshake that allows independent machines to merge into something greater than the sum of their parts.
And that precise symphony is happening all around you right now, completely out of sight.
Yeah.
I mean, whether it's the municipal pump raising water to your tap or the steel drive shaft spinning underneath your car, this delicate balance of material strength, calculated weaknesses like keyways, and mechanical interlocking is what physically drives modern life.
It totally shifts your perspective the next time you look at a piece of heavy machinery. But before we go, I want to leave you, the listener, with a final, slightly philosophical thought drawn from the very end of these engineering notes.
Oh, the Castellano section.
Yes. Buried in the back pages, way past the couplings and keys, there's this dense section on Castellano's theorem and strain energy equations.
For the mathematics of beam deflection, it actually underpins everything we've discussed today.
Exactly. Because throughout this entire deep dive, we've talked about these solid steel shafts and massive cast iron couplings as if they are absolute, unmoving, rigid objects. Like we oversize them to make them stiff. But Castellano's theorem mathematically proves that absolute rigidity is a total myth.
Right, it doesn't exist.
The theorem deals exclusively with what engineers call elastic bodies. The math shows that every single time a load is applied to that drive shaft, the metal is deflecting.
Even if you cannot see it with the naked eye, the physical structure of the metal is constantly shifting.
It's storing physical energy inside its crystalline structure like a tightly coiled spring. As the motor spins up, the solid steel shaft is imperceptibly bending, twisting, and warping under the load.
Wow.
So the next time you look at a massive, silent, heavy steel machine, remember Castellano's equations. That steel skeleton isn't a dead, unmoving object. It's elastic. It is breathing, bending, and holding back immense invisible forces. The physical world around us is just much more alive than it ever appears.